All right, Dan, you're up.
Thank you, Kelly, and thank all of you for joining us today on another session of Webinar Wednesday held on a Tuesday. Anyway, my name is Dan Honey, and today we're speaking about ASHRAE Standard 241, a standard that addresses the control of infectious aerosols. My name is Dan Honey. I've been in the industry for a number of years, since 1985. I'm going to be somewhat brief, as many of you have already seen this introduction a number of times, so I don't think we need to spend too much time on it. Anyway, my role at Veritech is as Director of High Performance HVAC Solutions and Educator. And since the ASHRAE Standard 241 was written in June of 2023, and its obviously stated importance, it was deemed necessary that we bring it forward in Webinar Wednesday to demonstrate how it's going to impact the design and laying out of HVAC systems in the future. Today, we're going to have a lot of material to cover. I'm going to be somewhat quick through the opening half of the session until we get into Standard 241, because it becomes a little technical. And if I do my job, hopefully I'll make those technical resources somewhat available to you and be able to communicate them. We're going to go into Standard 241. We're going to review the foreword, the purpose, and the scope. We're going to look at term definitions applied by the standard and compliance, and what is the importance of ASHRAE Standard 52.2 Informative Appendix J in the application of the standard. We're going to look at the meaning behind equivalent clean airflow for infection risk mitigation, air distribution and natural ventilation for creating clean air in an environment, air cleaning technologies, and the prescriptive measures by the standard for building owners to provide an assessment, planning, and implementation of the standard to existing and new buildings, as well as operation and maintenance, before we offer brief concluding remarks. So the COVID-19 pandemic. I think, first of all, to get an understanding of what was really driving the standard to be brought forward so quickly, it's necessary to just do a quick review of the CDC timeline and the resulting statistics. It was in December 12 of 2019 that a cluster of patients in China's Hubei province showed symptoms of an atypical pneumonia-like illness. And on January 7, 2020, public health officials in China identify a novel coronavirus. By January 19, worldwide, there were 282 laboratory confirmed cases, 278 of which were in China. On January 24th, we saw cases in the United States. In Illinois, there were 2 cases confirmed. And then on January 30th, 2 more cases were confirmed in Illinois without any history or travel history. People were not flying out of the country or whatever. This occurred within Illinois. This is January 20th or January 30th of 2020. On February 10th, worldwide deaths from the 2019 novel coronavirus reached 1,013. On April 4th, 2020, there were more than 1 million cases of COVID-19 confirmed worldwide, and by April 10th, 18,600 confirmed deaths and more than 500 confirmed cases under 4 months in the United States. By May 9th, the unemployment rate in the US peaked out at 14.7%. And by May 28th, the recorded death toll in the US was 100,000. By July 7th, the number of confirmed COVID-19 cases surpassed 3 million. By August 17th, COVID-19 becomes the 3rd leading cause of death in the US, and there were exceeded 1,000 deaths per day nationwide, with a caseload of 5.4 million people. By September 30th of 2020, the reported death toll from COVID reaches more than 1 million people worldwide. That's 8 to 9 months of time that we had such radical spread. On March 29th, 2023, the CDC reported that there were 6,859 deaths throughout the globe, and that is a staggering number. Those are the resulting deaths from COVID-19 that we know of. On June 8th of 2020, the World Bank stated that COVID-19 will plunge the global economy into the worst recession since World War II. There is a USC Schaefer report that projected that the total cost to the US economy will reach $14 trillion by the end of 2023. And the total US death toll through May 16th of 2023 was 1,172,000. It was rather interesting going back and reviewing these statistics because it begs us to ask the question, why is ASHRAE providing these rather compelling guidelines for future buildings that are to be applied, that are to be incorporated into codes and adopted by municipalities to bring forward into our built environment? Well, let's look back at the history of how our understanding of the means of transmission occurred. The original statements that came out of the CDC and the World Health Organization were that the main means of transmission were fomite transmission, surface to surface, hand to mouth, and large droplets. When people cough and sneeze and they expel large droplets of virally laden aerosols into the close proximity of somebody else. That provided, in the CDC and the World Health Organization's opinion, the means of transmission. However, on August 25th of 2020, a friend of mine put me onto an article in Time magazine by a Professor Jose Luis Jimenez, who said that COVID-19 is transmitted through aerosols. We have enough evidence, now it is time to act. And he went on to say, contrary to public health messaging, I, together with many other scientists, believe that a substantial share of COVID-19 cases are the result of transmission through aerosols. Goes on to say that fomites and droplets have dominated the everyday understanding of transmission. It is time for the CDC to act and to accept the fact that aerosolized transmission is a reality. The CDC finally, on October 2nd, 2020, acknowledged that COVID-19 can sometimes be spread by airborne transmission. So it took 10 months, 11 months, in order 10 months for the CDC and the World Health Organization to begin to recognize the risk of infection through long-range aerosols. However, ASHRAE had a different position. As early as April 14th, 2020, in the abstract of the position document on infectious aerosols, ASHRAE stated some diseases are known to spread by infectious aerosols. It goes on to say that the risk of pathogen spread can be affected both positively and negatively by airflow patterns in the space and by heating and ventilating and air conditioning systems. So ASHRAE was aware of the potential of aerosolized transmission of COVID-19 and was arguing how best to adapt an HVAC system to reduce the risk of infection. So let's review the modes of transmission, a topic I've covered a number of times, certainly during the pandemic, but it's very important when we start reading the opening portion of ASHRAE Standard 241. The means of transmission of COVID-19 occur when an infected agent is breathing, talking, coughing, or sneezing. If somebody's talking, they release 10 times more droplets than simple tidal breathing at a work desk. There's coughing that offers a ballistic trajectory where aerosolized droplets with viral loads can project 15 to 20 feet in a space. Then there is sneezing, where these virally laden droplets can be projected 25 to 28 feet in a space. And depending on the humidity of the environment, the droplets will either evaporate quickly in a dry environment or stay moist and large and due to gravity fall out of the air more quickly. So humidity does play an impact on the release of infectious viral loads into the atmosphere. To get an understanding of the size of particles we're dealing with sub-micron particles. And depending on the size of the droplet depending on the size of the droplets, will result in different buoyancy float times of those droplets within the air once they've been released. So the larger the droplets, the sooner those droplets will fall out of the air onto the ground and onto surfaces. The smaller the droplets, they remain buoyant longer. And if you have active viral desiccated agent free floating in the air, they can stay active and floating for 41, and I've read as high as 72 hours in an environment in an aerosolized state. Well, let's recall that the average size of a COVID-19 virus is 0.125 microns. So it has a long float time in the atmosphere. There was some interesting reading by Dr. Clifford Ho of Sandia Labs, who argued and brought to my attention, certainly, that even simple tidal breathing in a space of somebody who is sick with COVID-19, and for that matter, any cold or flu that somebody might be suffering from, that because the size of the droplets that are emitted during tidal breathing are small, they are more likely to evaporate and allow for active viral agents to be released into the atmosphere where they can be breathed in by other peoples who are within the environment. So Dr. Ho goes on to state that despite the lower viral load per exhalation event relative to coughs or sneezes, the persistence of the small aerosolized droplets, the continuous nature of breathing and or talking can increase the potential for transmission, especially in enclosed spaces with low fresh air exchange. And this brings us to ASHRAE Standard 241. And we're going to look at the forward, purpose, and scope of the standard so that we have an understanding of its context. In the foreword of the document, in the foreword of the standard, there are the following statements made. Airborne transmission of communicable diseases occurs. Engineering controls such as dilution, ventilation, filtration, and air disinfection can reduce the concentration of active pathogens in the air. The COVID-19 pandemic caused enormous personal, societal, and economic damage, as we demonstrated. This experience intensified discussion about the adequacy of existing IAQ standards, including code basis standards such as ASHRAE Standard 62.1. The catalyst for Standard 241 and its development was due to a discussion between ASHRAE and the White House COVID-19 response team that was asking and looking for new and better IAQ standards to reduce the risk of infection in environments, and not just for COVID-19. What about cold and flu season themselves, and how we move into our fall and winter seasons and submit ourselves to the increased rate of infections to various viruses that are around. The forward statements go on to say that the project scope of the ASHRAE board is to incorporate similar provisions to improve IAQ even further into the IAQ standards 62.1 and 62.2. So the language of Standard 241, it is the goal of ASHRAE, is to be drawn into Standard 62.1 and 62.2. And those standards are the ones that assign the ventilation rates to a building, how much outside air we bring into the building to avoid sick building syndrome. On December 6, 2022, the ASHRAE Board of Directors authorized development of a standard with the goal of publishing in 6 months, and that project committee did publish the document of Standard 241 on June 15th in 2023. And as I understand, it was the fastest standard ever written by ASHRAE, which does demonstrate some urgency. The foreword goes on to say under requirements that the standard will require from an HVAC system that at a minimum they comply with existing standards 62.1 and 62.2, and also ASHRAE Standard 170 by making sure that minimum ventilation rates or outdoor air rates are entering into a building. It establishes the requirement for a new expression. It expresses the requirement for infection risk management mode of operation, IRMM, that will be applied whenever there are higher levels of infection risk mitigation that are necessary due to a pandemic, due to perhaps maybe even an aggressive flu or cold season where a building owner wants to adopt the infection risk management mode to reduce the risk of infection. The infection risk management mode will allow for what is called the equivalent clean airflow rate to be attained at each person's occupied breathing zone. And I'll go into the details of these terms here shortly. There will be a requirement for an application of in-room air cleaners, and it provides a standard for those cleaners now that was previously lacking. There is a requirement for filtration and air cleaning that these technologies include laboratory testing and performance for safety and performance, and provide calculation procedures for determining the contribution of filters and air cleaners to achieve equivalent clean airflow requirements. A requirement for assessing, planning, and implementation of the standard to go into infection risk management mode. And it offers guidelines on operation and maintenance of these systems for building owners. The standard is also groundbreaking, according to the foreword, in these regards, as it introduces the concept of resilience into a system, where an HVAC system is able to move from a normal mode of operation into an infection risk management mode. And so that is identified as resilience, having the ability to adapt, to respond to immediate health crisis or situation. It will also be looked at for application to other modes as well, such as reducing wildfire smoke in expanded versions of the standard. At least that's the goal of the 241. And it'll provide what type of control requirements are necessary to provide the effective quantity of equivalent clean airflow rates at the breathing zone to reduce the risk of infection. It is groundbreaking in the regard that they are providing a major step in the direction of creating uniform and effective technology agnostic criteria for characterizing filter and air cleaner performance and safety. So the purpose of the standard is pretty much already expressed. In order to provide a resiliency in an HVAC system to adapt to an infection risk management mode that will provide equivalent clean airflow rates at the breathing zone. The standard does not address requirements for maintaining acceptable indoor air quality. It accepts that it may not substantially, in certain cases, reduce the risk of transmission, but this is key. This is key. It addresses only indoor long-range transmission, which is what we spoke about as the means of infection that was ignored by the CDC and the World Health Organization throughout the first 10 months of the pandemic. So this standard is addressing specifically that long-range transmission of infectious aerosols. The standard does not determine the conditions under which infection risk management mode should be invoked, but it does go on to say that each HVAC system shall have the resiliency to go into infection risk management mode whenever the authority having jurisdiction determines that during perhaps a pandemic, or when a building owner determines it for his building to reduce rates of infection, etc., etc. So as we move into the standard, let's look at terms and definitions. Let's define air cleaning. We associate air cleaning with particulate removal. Well, according to Standard 251, air cleaning is reducing the concentration of infectious aerosols. So when we use the term throughout this presentation, it's in relation to infectious aerosols, not necessarily PM 1.2, 2.5, and 10 micron sized particles. The authority having jurisdiction is the agency or agent responsible for determining compliance with this standard. There's another expression. Each building will have a building readiness plan, a plan that documents the engineering and non-engineering controls that the facility systems will use for the facility to achieve its goals. Standard 241 defines equivalent clean airflow as the theoretical flow rate of pathogen-free air that, if distributed uniformly within the breathing zone, would have the actual same effect on infectious aerosol concentration as the sum of outdoor air, filtered air, and inactivated infectious return air back into a space. Infection risk management mode is defined as the mode of operation in which measures to reduce infectious aerosol exposure documented in a building readiness plan are active. And then long-range transmission is defined as a disease transmission that is due to aerosols emitted by an infector who is not in close proximity to a susceptible occupant. So how are HVAC systems to comply with the standard? And I was rather surprised when I discovered this, because I've been presenting on the relevance of MERV filtration on a building system to reduce the risk of infection, as ASHRAE was explicit in its position document on infectious aerosols that a minimum MERV 13 rated filter be used, preferably MERV 14, if the system could withstand the static pressure gain. Well, under the prerequisites, again, the standard says that every building must provide the ventilation rates prescribed by 62.1, as well as standard 170 for healthcare applications. It goes on to say, and this is what's surprising, that the infectious aerosol removal efficiency, and that's a term we're going to visit later on as well, infectious aerosol removal efficiency of mechanical fibrous filters shall be assigned a value of 0 unless rated MERV A11 or higher when tested in conformance with ASHRAE Standard 52.2 Informative Appendix J. So I went to Standard 52.2 Informative Appendix J and was rather interesting about what I uncovered. In the foreword of 52.2, under passive electrostatic fibrous media air filters, ASHRAE offers this language. Some fibrous media air filters have electrostatic charges that may be either natural or imposed on the media during manufacturing. Such filters may demonstrate high efficiency when clean and a drop in efficiency during their actual use cycle. Therefore, the minimum efficiency observed during testing may be higher than that achieved during actual use. A pretty compelling statement. In my research for this presentation, I found CAMFIL to be a very useful web resource on filtration. CAMFIL offers a definition or an explanation of what the difference is between MERV ratings and MERV A filter ratings. It goes on to say that there is a critical component of MERV that is not being discussed nearly enough. Air filters can be produced with an electrostatic charge which acts much like a magnet and temporarily increases the particle capture efficiency on the 3 size ranges of particles tested, which are 1 micron, 2.5, and 10. A MERV 13 filter, for example, can drop to a particle capture efficiency equivalent to that of a MERV 8 filter within a short period of time. I thought that was very interesting. Well, what is informative Appendix J on ASHRAE Standard 52.2 that MERV-A filtration is based on. Appendix J presents a conditioning procedure to filter testing to determine the magnitude of the efficiency loss a filter may realize in field applications. When the Appendix J test is used, the data output obtained from the efficiency test procedure after the potassium chloride 10.7 test, that conditioning step then neutralizes the filter of its electrostatic charge, allowing for a MERV-A rating to be achieved. The appendix goes on to say that when the test in Appendix J is used, the data output value is thus differentiated from the MERV value. And it is done because it creates a condition at the filter that is more likely to be present throughout a filter's operating life in a real application. So be aware of that, because the purpose of Appendix J was to address the concern of efficiency, a filtration efficiency drop during the operating use of a filter. There was an interesting article in HVAC Engineering published when the updated 52.2 standard was initiated, published on August 1st of 2008. Goes on to say that the conditioning step in Appendix J will allow manufacturers to show results from two test procedures, MERV 14 and MERV 11A. And by the way, Appendix J to 52.2 is a voluntary test procedure. It is not a necessary test procedure. Well, it was until 241 has issued the language that it has. The HVAC article goes on to say it is safe to assume that MERV-A is closer to the efficiency of the filter in real-life application, and that it offers this advice, that when comparing air filters, look for both the MERVs and the MERV-A ratings. It is also to protect building occupants, choose a filter that is highly efficient in capturing particles of the 0.4 micron size. So for a commercial building, per ASHRAE's Epidemic Task Force guidelines of meeting MERV 13, use MERV 13, MERV 13A rated filters if you want to make sure that that filter maintains its efficiency throughout its operating life in a building. So the objective of ASHRAE Standard 241 is to provide an equivalent clean airflow at the breathing zone for infection risk mitigation. So what is equivalent clean airflow? ASHRAE defines equivalent clean airflow, again, in review from the definitions, as the theoretical flow rate of pathogen-free air that has the same effect on infectious aerosol concentration as the sum of actual outdoor air, filtered airflow, and activation of infectious aerosols by new technologies such as, well, UV lighting is not that new, but UV lighting, and now apparently ionization is becoming considered as a means of achieving that that deactivation of infectious aerosols. So according to the standard, a minimum equivalent clean airflow rate must be achieved at the breathing zone of each occupant to reduce the risk of long-range transmission. Well, how do you calculate the equivalent clean airflow rate to the environment, to a zone? Well, first of all, ASHRAE Table 5.5-1 in the 241 standard provides the prescriptive airflow rate, or equivalent airflow rate, clean airflow rate at the breathing zone when a building has been assigned to go into infection risk management mode. They're going to increase the equivalent clean airflow rate at the breathing zone. So to do that, you calculate the equivalent clean, you determine how much equivalent clean airflow is required per zone times the number of occupants in each zone. So to give you an example, if we look at an office space that has an occupancy of 10, maybe it's a conference room, to calculate the amount of ECAi air, or equivalent clean air, that is to be supplied to the space, take the 30 CFM per occupant as defined by the commercial retail CFM per person guideline, multiply it by its occupants, and you'll see that you would need 300 CFM of equivalent clean air at the breathing zone of those occupants when a building goes into infection risk management mode. Under paragraph 5.1.3, it also offers this, that if a group of occupants are involved in vocalization above conversational level, then the factor of airflow is to be doubled. So if for some reason there's karaoke going on in the conference room, then the airflow rates would be doubled up to 600 CFM. So let's look at the section of air distribution and natural ventilation. And we're going to look at clean air, that is to say, air free from infectious aerosols. So in order to understand how much clean air needs to be provided to each zone, depending on the effectiveness of the air cleaning technologies in removing infectious aerosols, this is the purpose of this section. How much air needs to be supplied depending on the technology applied to reduce the risk of infectious aerosols being propagated to the zone. Well, ASHRAE provides this equation, equation 6-1, that says the minimum clean airflow rate required at the breathing zone supplied by a multi-zone air handler is based on the summation of all the zones impact, and each zone will involve a calculation of the air zone fraction rate to the zone, the amount of outside air that will be delivered to the zone, the air cleaning system equivalent of clean airflow rate from the air handler itself for multi-zone unit serving all the zones. It'll also be based on the air cleaning system equivalent clean airflow rate by the air cleaning device, as well as any outdoor air that might be prevalent during a natural ventilation application. We're seeing throughout the industry more and more use of natural ventilation, so that there is a factor of bringing the amount of natural ventilation airflow into a building's calculation for how much minimum clean airflow rate will be required. So let's look at the graphics provided by the standard in figure 6-1 that show the sources of outdoor air and clean air strategies that are available to a space. There are multi-zone units that would serve a number of zones that can have air cleaning technologies embedded in them, such as their filtration technology, UVC lighting, possibly ionization strategies. There are other air cleaning technologies that are zone specific, that are served only by the return air from that one zone, and the supply air is then delivered to that zone. And then there are in-room air cleaning systems also available. So in order to understand the appropriate solution to serve each zone, ASHRAE 241 assigns that each zone shall have an air distribution category. Those categories are comprised of well-mixed environments, natural environments, cross-flow environments, downflow, and upflow. So it's rather interesting is that horizontal displacement ventilation is considered as falls under the category of natural. Section 6.3 also offers some guidance on natural ventilation, 6.4 on mixed mode ventilation, which is a combination of air handler conditioned air versus natural ventilation in a building. Well, we just don't have time to get into those sections, and nor would they immediately apply, certainly for us in the South, well, certainly in Phoenix, Arizona, and the Sonoran Desert. So applying air cleaning technologies that allow for building to supply allow for air handlers and air cleaning devices to provide the necessary clean air to a building to comply and meet the equivalent clean airflow rates, let's look at them and their applications. For the various technologies that are available in the industry, ASHRAE determines that each type of solution have a category. And the category of that device, whether it be UVC lighting or ionization or filtration, will be looked at where that device might be located in a zone, whether it's at the floor, wall, or ceiling, and how the air is discharged from that device, whether it's horizontal, up, down, or whether or not there is no discharge air, as you would see in upper room UV lighting. With that in mind, we can now look at what system might be permitted in which application. If you look at a well-mixed zone, you can see that ceiling downward flow air cleaning solutions are viable. Ceiling horizontal throw air cleaning systems are capable. For a downflow system, only ceiling downflow, not ceiling horizontal. For upflow systems such as UFAD, we look at flow of floor and upflow, et cetera, et cetera. So this table 6-3 gives you an understanding of, depending on the technology that might be applied to clean the zone of infections, that it be appropriately assigned based on this table's guidance. So let's look at ASHRAE Standard 241 and air cleaning. What is air cleaning? And this is a little complicated, so bear with me here. I'll try to navigate and find the language to make it accessible. So in the air cleaning section of the standard, section 7.2 offers a calculated effectiveness of air cleaning systems. That is to say, how effective is a technology in removing infectious aerosols? What percentage of clean air can come free of aerosols or of inactivating or actually containing infectious aerosols? So the effectiveness and safety of cleaning systems shall be determined by testing an air cleaning system in accordance with section 7 of the standard. And it also has language that says a responsible party designated by the authority having jurisdiction shall certify air cleaner operational performance and safety equivalence. So is that the local municipal authority who determines that during the startup and commissioning phase of a building? It also goes on to say that the manufacturer shall certify that air cleaning systems are effective and safe, appropriately applied in order to be used to meet the requirements under ASHRAE Standard 241. While there is calculative effectiveness for different types of air cleaning solutions, there is induct air cleaning systems that clean air and air handling for air handling units. And each air cleaning system located inside an air handling unit, ductwork or plenum, shall be assigned an air cleaning system flow rate based on the aerosols divided by 100 times the amount of return air being served by that system. So the infectious aerosol reduction efficiency, epsilon PR, shall be determined by a single pass test in accordance with section 7. So now building designers have a standard to lean on with the application of air cleaning equipment. That's standard 241, section 7, or normative appendix A, which I'll look at quickly here shortly. And they will help assure a design team that the equivalent clean airflow is being achieved by that device, providing it passes the testing conformance. So if we look at an induct air cleaning system to provide clean air from an air handler, ductwork or plenum, it's very simple. You take the infectious aerosol reduction efficiency, divide it by 100, times the amount of return air, and you will get the volume of clean air supplied by the unit to this space to see if it conforms to the requirement projected in the equivalent clean air table we discussed earlier. If you have multiple air treatment technologies or air cleaning technologies in an air handler, filtration, UV lighting, ionization, Maybe there's a combination of air handler plus in-room, depending on the risk of infection, occupancy, concentrations, etc. You can determine the infectious aerosol removal efficiency by either looking at one system, such as just using MERV 13A or MERV 14A filtration. You can look at two systems in an air handler, which would be your filtration system plus UVC lighting or ionization, or three systems perhaps. Anyway, you actually multiply each of the solutions in a system to determine the infectious aerosol reduction efficiency. So pretty interesting. What about one technology of air cleaning, mechanical fibrous air cleaning systems? Well, ASHRAE, the section 7.3 in the 241 standard offers an equation for making that assessment, where you take the fraction of the infectious aerosol between three different particle size ranges from 0.3 to 1 up to 10 microns, times the particle removal efficiency for each of those technologies. And then that particle removal efficiency is defined by table 7-1, which is the infectious aerosol removal efficiency for mechanical fibrous filters. And if you look closely, you'll see that after January of 2025, if you have MERV 11 or less, it'll be assigned a 0 value. Or I'm sorry, if it's below MERV 11, it'll be assigned a 0 value. So it will impact the volume of clean air supplied by that unit if you apply lower MERV rated filtration. Mechanical fibrous air cleaning systems can also be in-room. There can be HEPA, portable cabinet HEPA units that are actually used. There are residential in-room cleaners, and all of these are given effectiveness at air cleaning equations to determine how much clean air is provided to a zone, to see it as if it's in conformance to the equivalent clean air required by the standard. There are testing guidelines for air cleaning systems that inactivate infectious aerosols. The effectiveness and safety of air cleaners with technologies that inactivate infectious aerosols shall be determined in accordance with section 7.4. And this section actually addresses how these technologies can provide microorganism inactivation. And that's some examples either through mechanical fibrous filters. There are certain manufacturers who make electrostatic filters that will neutralize pathogenic agents. There's ultraviolet lighting, electrostatic, well, I already discussed that, electrostatic filtration, photocatalytic, ionizing air cleaning systems, et cetera, et cetera. What is interesting is that ASHRAE's previous language on ionization was that it is an emerging technology that needs to be given further study. Well, now that technology is being looked at, providing it meets the air cleaning effectiveness ratings as prescribed by a third-party testing agency to demonstrate its air cleaning capability. Section 7.4 also addresses induct air cleaning systems, induct ultraviolet germicidal radiation and other air cleaning solutions, as well as in-room cleaning systems such as upper room ultraviolet light and perhaps other directly delivered solutions into that space to reduce concentrations of pathogens. Normative Appendix A is used for determining an air cleaning system's effectiveness and safety as well, where testing of the effectiveness or safety elements of air cleaning systems fall within the scope of a national consensus standard. So what are those standards that Normative Appendix A is requiring for for measuring the effectiveness of removing infectious aerosols? Normative Appendix A is saying that ASHRAE Standard 52.2 must be MERV A ratings will be applied by 2025. It leans on ISO 16890, which is an international filtration standard. It relies on ANSI AHAM AC1. And then for UV lighting, ASHRAE Standard 185.1. These are the testing requirements for these technologies. For safety, in other words, will these technologies impact human health and well-being? They have to meet UL 2998 for ozone generation, which is that these air cleaning solutions cannot result in 5 parts per billion of ozone within the space. There's ASTM D8407, which measures formaldehyde, and as well as 14644, which is for the classification of air cleanliness with regard to particle concentration. So these are the standards that normative Appendix A states that air cleaning technologies need to conform to. Now, if you think that in order to design a building and to determine the total amount of equivalent clean airflow rates that each zone requires depending on air cleaning technologies, I could put your mind at ease, I think, and let you know that the standard offers under informative Appendix F equivalent clean airflow, an equivalent clean airflow calculator. It will allow you to enter all the variables of the various zones, and it will determine the amount of clean airflow that will need to be delivered. And then the question is which technologies can you rely on to give you validated and tested credible performance data to meet them. So we've got a little bit of time left, and we're just going to briefly run through other prescriptive measures Standard 241 offers. We're going to look at assessment, planning, and implementation. The standard calls for every building to have a building readiness plan that shall be created after the assessment, planning, and implementation phases to describe the engineering and non-engineering controls that the facility systems will use to achieve its target equivalent clean airflow. It will provide it provides a building readiness template as shown in the table to the left that demonstrates or documents the sequences of operations and the engineering controls that will go into operation to meet the infection risk management mode requirements. Section 8.1 has this language that the operation and maintenance procedures, including operating schedules, shall be provided and available to authorities having jurisdiction. Ventilation system operating schedules and airflow values shall be provided, and air cleaning technologies used to achieve equivalent clean airflow to the environment per the list of items shown on the slide. Assessment needs to be made for existing buildings. An existing building and its system shall be assessed for current operation and feasibility of potential engineering controls that contribute to the required ECAi. And I will say that I think Veritech is in a strong position to provide some assistance and guidance in looking at a number of air cleaning technologies that would conform to the intent of the standard 241. So operation and maintenance, there are guidelines for operating building readiness plans in the building. The section 9 of operations and maintenance says that there are modes of operation that need to be addressed and assessed, that need to be provided to the authority having jurisdiction. There's normal mode, there's infection risk management mode, and then what happens to a building when it goes into temporary shutdown. There are operating schedules to be provided and to be validated that they're being maintained. All of this will have to be documented. And it goes on in this section to explain flush cycles between occupied periods, occupant count during infection risk management mode, operation of various fan speeds, etc., etc. All of this is available in the standard. There's also a section 10 on dwelling units that we just don't have time to go into today. So it is now 12:55, and I'm just going to offer some concluding remarks with regard to this standard. The COVID-19 pandemic's rate of infections, I think, was somewhat staggering. And to think that by May of 2023, there were 1.1 million deaths in the United States by this pandemic is really causes one to pause and to reflect that there was perhaps $14 trillion of economic losses during the period of the pandemic. We demonstrated that one of the reasons why there was this surge of infection was not a full assessment available as to the means of transmission, because long-range aerosolized transmission was not taken into consideration, and that appeared to be a major pathway for infection with this aerosolized pathogen. So, however, do keep in mind that if you're looking for ways to really maintain a healthier environment to reduce the risk of infection, that ASHRAE's Epidemic Task Force was aware of the risk of aerosolized transmission 6 months before the CDC and the World Health Organization. And so they were way ahead of the industry and already had prescriptive measures to be applied. So ASHRAE's Standard 241 is a very valid guideline for reducing the risk of infection. So on December of 2022, the White House COVID-19 Task Force approached ASHRAE, and the ASHRAE Project Committee came together to write Standard 241. And the standard's objective is to reduce long-range transmission of infectious aerosols by designing HVAC resiliency into mechanical systems that can operate in an infection risk management mode that supply a prescribed amount of clean air to occupant breathing zones to reduce concentrations of aerosolized pathogens. Are there any questions? Obviously, there was an awful lot covered today in a short period of time, but please be aware that this presentation is meant to be somewhat comprehensive so that it could be a resource in the future, and it'll be available on Veritech's website in PDF form so you can look at it as just hopefully a quick frame of reference to give some understanding of what motivated the generation of the standard, its sense of urgency in being produced, and what we understand of its application being brought into municipalities in the writing of their codes. So, any questions?
We do have a couple. And as Dan mentioned, this, there's a lot that goes into this. So that, barely scratching the surface. We'll keep this conversation going. So, look in our newsletters for more information about it, any updates, any new little tidbits, as well as our social media platforms. So it's just so much to try and fit into 1 hour. So just keep your eye out for more information coming. So we do have a couple questions. When will Standard 241 become widely adopted, and what does the path to adoption look like? Do you know?
The way I understand the standard is that it will be adopted into Standard 62.1. When it becomes part of 62.1, it now becomes part of code. And it'll be up to the authority having jurisdiction in each municipality to determine which of the prescriptive measures of 241 will be applied. But until it's actually applied into 62.1, I don't see a pathway, and maybe I'm wrong, I don't see a pathway for it to become code for new construction.
Okay. And so then, Tamara, that kind of hits on what you're saying, that you have a feeling that you'll be seeing this on the authority having jurisdiction side soon. So just keep your eye out for when it gets adopted into 62. And I think we'll give you guys updates on that as we start seeing.
We're going to be, well, please subscribe to our newsletter, because Kelly and I really do monitor latest developments in the industry. And I can't help but think that the implementation of 241 in the municipal codes will become more prevalent in the near future.
Yeah. Absolutely. Will ASHRAE 241 be referenced in the model mechanical code, codes in the base code, or as just an appendix?
I don't know. I don't know how the mechanical code has responded to standard 241, and I haven't looked at it. Maybe there is a response, but I haven't looked into it.
Okay, and I'm going to save all these questions so that if we do find out any information, we can let you know specifically on these questions. That is all the questions that have come in. I know if you guys do have questions, it might be, you know, where do you even begin to ask your questions? So if you think of anything after this, go ahead and, you know, always email me, email Dan, email the contact that you always talk to at Veritech. And we can continue answering these questions, and we'll just keep you updated as new things start happening with this standard.
Absolutely. We're going to be following it very closely.
I'm just going to monitor the chat for another minute. So if you have any other questions, if you do need to drop off, we do understand it is 1:01 p.m. here in Mountain Standard Time. So feel free to jump off or stay on if you want to come off mute and chat with Dan and ask any other questions. But those of you that are dropping off, yeah, thank you. And Dan. Yeah. Thank you for attending. We appreciate it. And it'll probably be on a Wednesday next month. I know Tuesday was weird. Now my whole week is thrown off. I don't know what day it is.
We'll keep our fingers crossed. Thank you, Kelly.
Thank you, Dan. And I don't see any more questions coming in, so we'll go ahead and end this. Thank you, everybody, for attending, and I will send out the PDHs and the recording link here shortly, and keep an eye out for March's webinar Wednesday announcement coming soon.